Okay, so exam 4. The reason it came up so fast is because we put off the last one a week. Now we're getting back on schedule. So exam 4 is next Monday. That would be the 20th, 11/20. And I don't know, I would be willing to postpone this one too, but then it's like, no one wants to have that hanging over their head on Thanksgiving and stuff, do you? Maybe you do. You might be the only one. Okay. Okay. So not even Shimri. Well, the only one that you have out is exam 3. The other ones I've given back. That one, I don't know. It might be ready. I don't know. I don't think I can probably get it done by Monday. Let's not do that. This test that's coming up is everything up through circular motion. And by the end of class today, you'll be ready to do all the circular motion problems. Yeah, any questions about the test? So we'll work on circular motion today, and then Wednesday, if you have questions about problems or whatever, bring them to class, and I can go through some problems. And we won't go on to the next topic until you're done with questions about circular motion. Yeah, I think that's how it is. All right, well, so last time I gave a set of 7 steps for circular motion problems. There was one, so this set of steps works for uniform circular motion where the speed is constant and non-uniform circular motion where the speed changes. There was one specific type of problem where these steps are not the way to go. Anyone remember what that was? Tetherball, yep. Except tetherball. So I'll go through a non-uniform circular motion problem, and then I'll talk about tetherball problems. We'll go through an example, and then we'll look at the clock, see what time it is, read it off the hands of the clock. Okay, so except tetherball. So let's say there's this kid, this little wiener kid playing at the park. He's on one of those carousels they don't allow into parks anymore. Believe me, I fell off many of those very hard. Yeah, like when I talk about this little wiener kid, it's like my therapist says it helps. So he's on this carousel. And this kid has a mass of 15 kilograms. And his speed is 2 meters per second. That doesn't sound so bad. And the radius of this carousel is 2 meters. Let's crank the speed up a little. And let's calculate first, what's the acceleration? And second, what's the horizontal force required so he doesn't slip? And then third, let's do one where if at this instant the kid is speeding up at a rate of, let's say, 10 meters per second squared, what's the acceleration? And the horizontal force required so he doesn't slip. Okay, so for A and B, we're going to do a uniform circular motion problem. We're going to assume that the speed is constant. And then for part C, we're going to now assume that the speed's changing and see how that works into this problem. Okay. So what's the first step? First, is it a tetherball problem? I haven't talked. It would be pretty weird if this thing here was a tetherball problem. So let's say no. And so what's the first step if it's not a tetherball problem? Yeah, choose a view. So what view do we want to take for this problem? Yeah, top-down view. And by the way, remember that top-down view means that weight and often normal forces, as long as the surface is flat, won't appear in our calculations. Okay, and then, okay, so this is the view. And then we have to choose a point to analyze. What have we done? We've done the right side, the bottom, so let's do one. Well, let's do one at the top. I don't know, why not? So here's the top of the kid's head. There's his legs. And it doesn't say anything about which way it's spinning, so let's say this way. What's the second step? Oh, we already did that. What's the third step? Okay, so this is the direction of the centripetal acceleration. And the magnitude of the centripetal acceleration is equal to the speed squared divided by the radius. The speed was 4 meters per second. So that's 16 meter squared per second squared divided by the radius, which was 2 meters. So 8 meters per second squared. That vector is in the negative y direction. So the total centripetal acceleration vector is 0, negative 8. And for this first part of the problem, we're assuming that speed is constant. So there's no tangential acceleration. And so the total acceleration vector is 0, negative 8. So that's part A. And now for part B, we want to figure out the horizontal force that's required for him not to slip. Well, if we're going to, so we know some stuff about accelerations. We want to figure out some stuff about forces. So the way to do that is always through Newton's second law. So I want to start with a free body diagram. That's like the top of his head and his shoulders and his legs, you know, top view. And what forces are acting? Well, really, there's a weight force. But that's not going to show up in this coordinate system because that's into the page. And there's a normal force that's coming out of the page, but that's not going to show up. And so the only things that are going to show up are, we're trying to calculate the force vector in the horizontal plane that's required for him not to slip. So let's just say we don't know the direction of the force. We're going to have some unknown x component, I'll call it fx, and some unknown y component, fy, and then that's it. Yes? Well, friction is what would apply those forces. Yep. So that's a good thought. This is static friction, and so we haven't really talked about dealing with that as friction, but we're just going to say we know that there's some force that's in the plane. We don't know what the components are, and we're just going to calculate both of those components. So Newton's second law says Fx Fy is equal to the mass, 15 kilograms, times the acceleration vector, 0, negative 8. So the x equation says Fx is equal to 0. And the y equation says Fy is equal to 15 times 8 is negative 120. So altogether, that horizontal force vector is equal to 0, negative 120. Any questions about that? Okay, so now we're going to do the same problem, but now the speed's changing. So we're going to have to deal with tangential acceleration. So for part C, let's just do this whole thing again. There's the path and the coordinate system. And here's the point that we're looking at. The centripetal acceleration still points this way. The magnitude of the centripetal acceleration is still 8 meters per second squared. And that's in the negative y direction. So the centripetal acceleration vector is 0, negative 8. Now this time we have to deal with the tangential acceleration. All right, so in order to do that, we have to think about the direction of the tangential acceleration. I did this problem saying that this is rotating this way, right? So which way would the velocity direction be pointing when the kid's at this location? Yeah, so the velocity is like this. And if the velocity is that direction and the kid is speeding up, which direction is the tangential acceleration pointing? Same direction, because that's a parallel. So let's see. So this is the direction of the tangential acceleration. We know the magnitude of the tangential acceleration was 10. 10 meters per second squared. Well, the direction is in the positive x, it's in the positive x direction. So the tangential acceleration vector is positive 10, 0. And so now to get the total acceleration, we just add those two parts together. So that's 0, negative 8, plus 10, 0. So 10, negative 8. And now we want to figure out the horizontal force. So free body diagram again. You think anything changes with this free body diagram? Well, yeah, no matter what, I mean, you deal with the weight force, and then you just imagine looking for where there's contact with the outside world. The only contact is where he's sitting on the carousel. So there's a normal force coming out of the page, and then an unknown direction of horizontal force. So I'm still just going to write that as Fx, Fy. You might as well do it that way, because if it's negative, that'll just come out in the calculations. So there's no reason to guess about it. So Newton's second law says Fx, Fy is equal to the mass, 15 kilograms, times the acceleration, 10, negative 8. So the x equation says Fx is equal to 150. And the y equation says Fy is equal to negative 120. And so altogether, that horizontal force is equal to 150 negative 120. Okay, so say that that horizontal force is just totally provided by friction, that he's not holding on to anything. Anybody have a idea how we would figure out how plausible this is? Like, is that too much force for him to stay on? Is he going to definitely slide off? Or like, how would we get into that calculation? Yeah, you could. That's a really good thought. Choose a new plane, draw a free body diagram. For us, I'm going to just skip all that and just say, like, we'll never do anything more complicated than this in the other plane. We'll just say that that force is provided by friction. The normal force is just equal and opposite to the weight force. So we'll just say, we'll just always assume that the normal force for these problems is just equal to the kid's weight. And the friction force, like a friction force that can be applied, is equal to the normal force times the coefficient of friction. Okay, so the normal force is just going to be equal to 15 times 9.81. So 147.15 newtons. And then the force of friction maximum for static friction is just equal to the coefficient of friction times the normal force. So what we need to do is, I don't know, let's choose what do you think is a good coefficient of friction for human butt? Let's say 0.3. Or let's say he's wearing leather pants and it's 4. So the force of friction max is equal to 0.4 times 147.15. Can someone calculate that? Ooh, wait, 58 point, is that right? 0.86? Yes. Okay, so now what we're doing is just comparing the force that's required for him not to slip to this maximum force of friction and seeing which one's bigger. If the force that's required for him to stay, to not slip, is bigger than that, then he's going to slip. Yes? Yeah. Yeah, you can just take something that can measure a force that you apply. And actually, a spring is a pretty easy way to do it. And push on the thing until it starts to slide. Measure the weight of the thing. So you use that to measure the normal force. And then whatever force you had to apply is just equal to the coefficient times the normal force. And then you just solve for the coefficient. So it's pretty easy. Okay, so the maximum friction force that could be applied, assuming that his coefficient of friction with the carousel is 0.4, is 58.86. Both of these two, what we would be doing with those required forces is calculating the magnitude of those to compare. But we don't even have to do that here because both of those two forces have single components that are bigger than 58.86. So he's going to fall off. Too bad. Any questions about that one? Okay, let's do one more like this. Okay, so let's say you have a ball on the end of a string, and you're swinging it around in a circular path. Let's say this time it's going this way. Oh, can we do this? Yeah, let's say this is where we're going to analyze it. At the point P, the speed of the object is, let's say, 10 meters per second. Slowing down with an acceleration magnitude of 9.81 meters per second squared. The string has a length of, let's say, 3 meters. And we want to know what's the tension in the string. Oh, we need the mass of the ball too. So let's say the mass is 0.10 kilograms. Okay, so what's the tension in the string at that point P? We want to choose a view where we can see the circular path. So there's the view. And the coordinate system is this. The point we're going to look at is this. Centripetal acceleration points this way. It's going, yeah. The magnitude of the centripetal acceleration is 10 squared divided by, how long was the string? 0.3. So that's 33 1/3 meters per second squared. To put that in a vector, the centripetal acceleration vector is in the negative x direction. So the centripetal acceleration vector is negative 33 1/3, 0. Now we have to figure out the tangential acceleration. Yes? Yes. Thank you. So 333 1/3. Now we have to think about tangential acceleration. Which direction is the velocity at this instant? Up. So there's V. This is slowing down, so which way is the tangential acceleration? Down. And that's in the negative y direction. So the tangential acceleration vector is 0, negative 9.81. And so then the total acceleration vector is just adding those two up. So negative 333 and a third, negative 9.81. Meters per second squared. Now free body diagram of the ball. Okay, so now we have to think about what our view is. Are we looking at this from above or from the side in order to see the circular path like this? Okay, it's from the side. So this time we are going to see gravity in this picture. So there's a weight force down of 0.1 times 9.81, so 0.981. And then at this instant, the string is horizontal, so the pulling force is this way, and the magnitude's T. And Newton's second law says, so this force T is in the negative x direction, so that's negative T0, plus the weight force of 0, negative 0.981. Is equal to 15 times the acceleration. Yeah, sorry, thinking of the kid. Okay, 0.1, negative 9.81. The x equation says negative t is equal to negative 33 and a third. So t is equal to 33 and a third newtons. Well, that's all we were asked for. The y equation says, well, it works out, so it says that, gives us a little confidence that we thought about it right, but negative 0.981 is equal to negative 0.981. True. This is the answer. So in order to spin a ball around that fast, at that instant in the motion at least, you need a string that can withstand 33 newtons of force. Okay, so let's do a couple more examples with this one. Where do you think, so if we're trying to figure out the most force that the string has to withstand, where do you think that would be in the path? Okay. It is going to be, so that force is going to be think about it this way, like if like when you do giant swings around the bar? You really do those? Good job. But anyways, can you imagine where, like, where are you most at risk of your hands peeling off the bar? That's the question. Like, imagine doing it at the park, showing off. Like, are you most nervous about your hands about flying off the bar as you go over the top, or as you go down the side or up the side, or is it at the bottom? Yeah, the bottom is where that force is going to be biggest. Is that sort of makes sense with your intuition about that? I can show you why that is as we go through the problem. But so let's figure, and then what do you think is going to be the point where there's the least tension in that string, where there's the least stress on your hands as you go around? The top, yep. So let's do this again at the bottom and the top and calculate what those tension forces are there. Okay, so first at the top. And by the way, remember we did something like this in lab where I said that when things are under the influence of gravity like this, if there aren't any other things making it speed up or slow down, things are always speeding up when they're going down and slowing down when they're on the way up. And so almost through the whole motion, something that's going in a vertical circle like this is either speeding up or slowing down. But the bottom and the top are the 2 points where that's not happening. So these are actually both going to be uniform circular motion. At those 2 instants, there's no tangential acceleration. Okay, so at the top, this is the point that we're looking at. The centripetal acceleration is down. It would change speeds a little bit. I can figure out how. Just a second. So we know that we'll talk about how to do this later. But I said it was going 10 meters per second, right? Okay, so cancel those. Can someone tell me what that number is? 50 plus, I can do this. 50 plus 1.4715, 51.4715. And so up at the top, it would be, say, v squared over 2 plus 2.943 is equal to 51.4715. Can someone tell me what v is? This isn't part of the problem. I should just be doing it quietly, but I'm just used to talking while I do this. Can someone calculate what that v is? Yeah. So at the top, the speed is 9.85 meters per second. So the it's slowing down the whole time it's going up. So it's going to be at its slowest right at the top, and it's speeding up the whole time it's going down. So this is the speed at the top, and then the speed at the bottom should be a little higher than 10, and that's going to be so v squared over 2 is equal to 51.4715. So that'll give us v at the bottom. Can someone calculate that? $10.15. Okay, meters per second. So all that was just to figure out what this speed was at the top and this speed at the bottom. And we haven't talked about how to do that or anything. I didn't have those. So now we're going to use those speeds and the fact that there's no tangential acceleration at the top or the bottom to figure out the tension in the string at those points. So this stuff is aside. So the centripetal acceleration magnitude is equal to v squared over r. We're doing the top first, so this is 9.85 squared divided by, it still has the same radius of 0.3. So what do you get for that? $323.41. That's in the negative y direction, so the centripetal acceleration is negative 323.41. There's no centripetal, no tangential acceleration, so that's also the total acceleration. Now, free body diagram. There's a weight force of 0.1 times 9.81, so 0.981. And then the tension force is going down 2, and that has, we'll say that the magnitude is T. And now put it in Newton's second law. And you get negative 0.981 plus negative T is equal to the mass times the acceleration, negative 323.41. The x equation doesn't give us anything. The y equation says negative 0.981 minus t is equal to negative 32.341. And so t is equal to 32.341 minus 0.981. What do you get for that? 31.36 newtons. We expected that at the top, the tension in the cable would be less than on the side, and it was. The reason it's pretty close to the same is because this is just spinning so fast. If it was spinning more slowly, we'd get a bigger difference. Any questions about that one? And then at the bottom, that's the view. That's the point we're looking at. The centripetal acceleration is this way. Magnitude of the centripetal acceleration is the speed squared. So that's 10.15 squared divided by the radius, 0.3. And what do you get for that? .41 meters per second squared. That's in the positive y direction, so the centripetal acceleration vector is 0, positive 343.41 meters per second squared. There's no tangential acceleration, so that's also the total acceleration. A free body diagram of the ball has a weight force down of 0.981. This time the tension is up. So Newton's second law says 0 positive t plus 0 negative 0.981 is equal to the mass, 0.1, times the acceleration, 0 positive 343.41. Again, the x equation doesn't give us anything. The y equation says t minus 0.981 is equal to 34.341. So what do you get here for t? $35.321. 322 newtons. And of the three, that's the biggest tension. And when's the next Summer Olympics? Is that not till 2020, I guess? Okay, we can't wait that long. Go to YouTube and look for gymnastics videos. What you always see when people are on high bar, high bar is the one where they're like swinging around in circles. Okay. And they do these tricks where they like fly over the bar and do flips and then catch back on. And when they do that, there's obviously a big risk that you're not going to get a good grip again when you catch back on. And so there's two ways. Okay, go to YouTube and search high bar fails or something. Okay, and there are two ways these are going to happen. well, maybe 3 ways. Mainly 2. Let's say 2. So one, the one that we don't care about, is they flip and then they come off and they can't reach the bar. Okay, and then those wipeouts usually aren't too bad. They just, they land back on the mats on their stomach or on their back or something, but they're all right. But the ones that look really dramatic are the ones where they do catch the bar, but they don't get a good hold on it. Okay, and when that happens, they are able to hang on to the bar the whole time through here, but as they're going down, the tension required is increasing until they get to the bottom where it's at a maximum. And right when they get to the bottom, where they're dealing with the most force they have to, they lose their grip. And what direction is their velocity when they lose the grip at the bottom of this circle? So if they're here on the circle, their velocity is straight this way, and they go flying and flipping off this way as they wipe out. Their coach tries to catch them, and they knock the coach down, and they all, it's really good. They have mats everywhere. They're fine. I'm sure it does hurt, but they have a lot of adrenaline, I'm sure, when it happens too. When that kind of thing happens, I used to be a gymnast, a really super bad one, until 7th or 8th grade. And like when you get hurt like that, like everyone runs over and they're like, "Oh my God, are you all right?" And you're just like, "I have no idea if I'm all right." You're just like, you're sort of shaking. You feel totally fine. And then it's like 20 minutes later when you're like, "Oh, I broke my back," or whatever. Okay, any questions about that? Okay, let's do a tetherball problem. Okay, so tetherball problems. And what I'm going to call tetherball problems, it doesn't just have to be a ball attached to a string when you're playing tetherball. It's any horizontal circular motion where the only support is a cable. So if you have a pole and a ball on a cord and it's going around like this, that's a tetherball problem. That's actually literally tetherball. But, it could also be this muscle guy swinging an axe around on a chain, That's also tetherball. But don't play tetherball with that. Okay, so for tetherball problems, in tetherball problems, there actually is no way to have the speed change. Well, the speed can change because of friction or whatever. But the assumptions that we're making, it's always uniform circular motion. Speed of the object doesn't change as it goes around the path. We can try that in lab too. You can't make it change. So the speed of the object can't change. So it's always uniform circular motion. And so what does that give us that we can use? The fact that it's uniform circular motion. Yep. Exactly. There's no tangential acceleration. Yep. Okay, so here, in these cases, these problems only, so in every other kind of problem, we take a view of the problem where we can see the circular path. In this one case, we're going to take a side view, so we're not going to be able to see the circular path. The rest of the approach is the same as before. Okay, so let me try to do this example pretty quick, and then hopefully we'll have time for me to find a good gymnastics wipeout. I used to, I didn't, I was very physically ungifted, but I was also very emotionally unprepared to be a gymnast. And around the time I quit, I would start getting sick to my stomach the day of practice, all day during practice, because the stuff was just starting to terrify me so much. And I remember one time my coach was like, okay, well, let's work on these tricks. I started to go, and my coach is spotting me. He's like, turn around, go the other way, because if you peel off the bar, we don't want you going over that railing. We were up on the second. I'm just this doesn't seem like a good idea at all. Oh, yeah. Oh, yeah. But, yeah. That's just like me. Okay, so let's say that we have a ball going around the circular path. And this isn't the ground or anything. This is the only thing supporting it is this cable up above. Let me make that dotted. And let's say we know that this angle is 45 degrees. It doesn't look like it, but. And let's say that we know that the length of this cable is 0.25 meters. And we want to figure out two things. Also, let's say the mass of this ball is 0.1 kilograms again. First, we want to know the tension in the string. And second, we want to know the speed of the ball. Okay, so first, just intuitively, does it make sense to you that this is enough information to figure out the speed of the ball? Imagine that you're spinning this thing around. What would happen if you increase the speed of the ball? What would change here? The tension would change, but of the stuff that I gave. The angle, yep. So this is enough information for us to calculate the speed of the ball because I gave that angle. Okay. All right, so this time we're going to take a view over here. The coordinate system I'm going to choose is that. This angle is 45 degrees. The centripetal acceleration. The centripetal acceleration doesn't have anything to do with that cable. It only has to do with the circular path. So it's pointing straight towards what I have as the origin, this way. Magnitude of the centripetal acceleration is the speed squared divided by the radius. Do we have enough information to figure out, well, we know we can't, we're going to have to use this to solve for v, so we know we don't know that. Do we have enough information to figure out r, the radius? Yeah, we know that this is 0.25. R that we want is this. And so we can use the fact that, so R over, well, you can just always use this equation this way. R is equal to 0.25 times the cosine of 45 degrees. Which is 0.176. So the centripetal acceleration vector is v squared over 0.176. Because it's a tetherball problem, we know there's no tangential acceleration, so the total acceleration is this too, v squared over 0.176. Oh, that's in the negative x direction. There's a 0y component. And now, free body diagram of the ball. Yeah. So the forces on the ball, there's a weight force of 0.981 and a tension force like this, parallel to the cable away from the ball. And so Newton's second law says P times the cosine of 135 degrees, P times the sine of 135 degrees, plus 0, negative 0.981, is equal to the mass of the ball, 0.1, times the acceleration, which is negative v squared over 0.176, and then 0 for y. So the x equation says negative 0.7071t is equal to negative v squared over 1.76. I just combined those numbers. And the y equation says positive 0.7071t minus 0.981 is equal to 0. So we can use the y equation to solve for t. What's 0.981 divided by 0.7071? 1.387 newtons. And then we'll take that value, plug it into x, the x equation, and we get negative 0.7071 times 1.387 is equal to negative b squared over 1.76. You can cancel the negatives. And what do you get for v? V is 1.314 meters per second. Any questions about that? So those tetherball problems are really always the same. You'll set it up the same way, have the same equations, solve for the same two things. Okay.